and let us hope that there are no interruptions today. Yeah. So today we are going to see something called as DTL, that is diode transistor logic, in which there is some kind of RTL study also, and then we will move to TTL and then CMOS. So there are some sums based on this part, so you should be able to solve those sums, and they are not really very difficult. So like always, there is a procedure, and you need to understand that particular procedures. Okay. So the very first thing that we are going to see today, Karthik, I'm audible and my slides are visible. Just confirm that
Yes, sir.
my voice
You're
is.
audible and yeah. And your screen is also visible.
So what we have here is DTL, that is diode transistor logic. So we start off with something called as DTL. Now in our syllabus they have just said that we should know TTL and CMOS. Okay, but to understand TTL we need to understand something on DTL first. Something on DTL first. So my today's discussions and diagrams are mainly from the book by Yarbrough, and it is a Senage publication book. So this thing is very well written in this particular book, that is Senage publication, and yes, it starts with DTL and it moves right up to CMOS or probably C square MOS and so on. So that is how we are going to go ahead. So first part of study is TTL, and in the first part of study, that is of TTL, we are going to see diode transistor logics. That is what we are going to see. Now you can see, uh, I told you that last time we have seen different kinds of logics. So we saw RTL, we saw DTL, then we saw TTL, then we saw ECL, and so on. We had CMOS, then MOS, then we have many other also actually. We have C square MOS, then we have pseudo NMOS, pseudo. Then we have something called as transmission gates. Then we have got pass transistor logics. So these are, there are many such logic families. Okay, so as you know that because of the number of these logic families, the syllabus is just focused on TTL and CMOS. But as you move through electronics engineering, you will touch each and every one of them. So as far as digital design is concerned, we will be initially touching only TTL and CMOS. TTL because TTL ICs are available in our lab, and mostly they are available in the market very easily also, and that is why the study of TTL is important, as well as study of CMOS, because the current technology is CMOS. So that is why we should know CMOS, and sometimes we need to interface the two together. Some part is good in TTL, some part is in CMOS, so we need to integrate both of them, and that is the reason why we need to study both of them. Now today's discussion is slightly going to be on BJTs. Okay, so there will be BJTs in our discussion. So before I go ahead, I want to know what are the different modes of operation of BJT. Anybody can answer this question. what are the different modes of operation of a BJT. So I hope you know that BJT is a three terminal device, and that is emitter, then we have base, and then we have a collector, and there are two junctions J1 and J2. So based on the situation in the junctions, we need to identify whether the, so if J1 and J2 are both forward biased, we say that BJT is operating in saturation mode. If J1 and J2 are both reverse bias, then we say that the BJT is operating in cutoff mode. If J1 is forward biased and J2 is reverse biased, then we say that the BJT is in forward active mode, and when J1 is reverse biased and J2 is forward biased, we say that the BJT is in reverse active mode. So when either of the junctions is reverse bias and forward bias respectively, we say that the BJT is going to be in active mode. Which active? Forward active or reverse active? That is the case. So Karthik has given the answer active, saturation and cutoff. That is true when you look at BJT configurations. Here I am looking at a simple BJT. There is only BJT and nothing else. But when you look at biasing circuits, that is when you try to model the BJT as a two-port network by making one terminal common, I think Karthik, you are referring to emitter mode, and that is the time when we can talk about active, saturation and cutoff. Okay, but the discussion is going to be something different. The transistor, as we saw yesterday, has actually evolved from from the concept of a diode only, and then later on we saw that it is easier to make a diode with the help of a transistor rather than actually making a PN junction. So that is the thing that we are taking forward. Now here you can see two diodes, that is D1 and D2. This is VCC. So let's say if this is 5 volts. Let's say this is 5 volts. So the voltage at this point will, so the current flowing is going to be 0 for the time being, because you can see that there is no closed path available as such. There is no closed path. So that is why if the voltage drop across R1 is 0 for the time being, what you will have here is 5 volts, and here also you will have 5 volts. So depending on what you apply at VA and VB, diode D1 and D2 will be forward biased. So you can see if VA is 0, let's say if VA is 0, cathode is at a lower potential as compared to anode. So cathode is at a lower potential as compared to the anode. Because of this, the diode D1 will be forward biased. If VA is equal to, let's say, 5 volts, then the potential difference between anode and cathode is 0. So it should be at least 0.7 for D1 to be on. That is why we say D1 is going to be reverse bias. So as you know, in forward bias, the diode operates extremely low resistance. So basically it's like a wire, and in reverse bias it gives me extremely high resistance. So that is why extremely low resistance means short circuit, and extremely high resistance is something like open circuit. So a device which short circuits and open circuits on application of VA, that is the voltage at one of the terminals, then that circuit can be used, or that device can be used as a switch. So you can see here, right in this diagram, the diagram next to this, there is going to be a switch. So I'll just rub off this thing. So we can use diode as a switch. So this is the actual use of the diode as a switch. Now I have written that the circuit that is given to us is actually working like a AND gate. How? Let us see that. So as you can see that there are two inputs, VA and VB. So we are looking at a two input AND gate. We are looking at a two input AND gate. Now here, how does it actually behave like a AND gate? Let us look at that. So we have VA and VB. So let's give VA as 0, 0. So if I give VA as 0 and VB as 0, then so before I go ahead, I want you all to copy these two circuits. Once you are done, then we will go for the further explanation. I want that this should be there in your notebook. And today there will be a lot of circuits, so please draw those circuits. I will wait for you till you draw it. So please draw this circuit. Then we will look at the working of the transistors. How this circuit actually behaves as an AND gate. That is what we will see. Once you are done drawing these circuits, these two circuits, just write done in the chat box. So today I am going to ask questions to everybody serially, and starting with Adhyay Jadhav. So Adhyay, can you unmute yourself? Adhyay Jadhav.
Hello.
Yes. Yes, Adhyay, I can hear you. Yeah. So I will ask you some questions, Adhyay. You just try to answer them. Okay, based on the circuit that is there on your screen. Is it okay?
Okay, sir.
Yeah. And can you tell me? So I'm drawing a graph. This is I and this is V. What is this point called? What is this point called?
Sir, sir, cut off.
It is not called as cutoff. It is called as. Can you again try?
तो इसका
It is called as the contact potential of the diode. It is called as the contact potential of the
सर
diode.
सर नी वोल्टेज नहीं, नी वोल्टेज.
Yes, it is also called as knee voltage. Correct. So that knee voltage is the formula for that voltage is Kt by Q ln
Yes sir.
Na Nd upon Ni square. Okay.
Yes sir.
So by controlling the doping, we can actually change this point to from 0.7 to 0.5 or probably 0.3 or even probably 0. So once that happens, we will actually move from a practical diode to an ideal diode. So okay, Adhya, you can mute yourself.
Okay sir. Thank you.
So I hope you all have drawn this diagram, or you are still drawing. Asmita, have you drawn this diagram?
Yes, sir.
Okay. Now the further slide is going to be the breakup of this diagram. The second one, I am going to break it up into 4 more diagrams. So let's see that. First one is, that is case 1. You can see both A and B voltages are 0. So here you can see VA is 0 and VB is also 0. Okay, Asmita, can you tell us diode D1 and D2 whether they are forward biased or reverse biased?
Sir, they are forward biased.
Are both forward biased?
So both are forward biased.
D1 is forward biased and D2 is also forward biased. Okay, fine. Why do you feel that they are forward biased, Asmita?
So because the anode is connected to the positive and cathode to the negative.
Uh, okay, don't say positive and negative, because as far as I can see, cathode is connected to ground, it is 0.
Yeah, sorry, ground. Sorry.
Okay, so you can say that the potential difference between the anode and the cathode is 0.7 volts, and that is why, or probably more than 0.7 volts, and that is why diode D1 and D2 are on. Okay, so as you now move ahead in the technical courses, we need to slightly improve on the definitions of our devices. Initially, I know that it is taught to you that way only, that it is positive and negative, so diode will be forward or reverse. But it is not positive and negative, it is the difference. If the difference is more than plus 0.7, then we say that the diode is forward biased. That is good. Okay. Next one is Akshay Sayonki. Can you unmute yourself? Akshay. Okay. Amit Chaudhary. Amit Chaudhary. Anurag. Karthik, please note these names: Akshay, Amit, and Anurag.
Yes, sir.
Anusha.
Yes, sir.
Okay. Can you tell me diode D1 and D2 are in which mode of operation?
So diode D1 is in forward bias and D2 is in reverse.
Forward and reverse. Okay. Can you tell me why D2 is in reverse bias?
So because the N terminal is connected to plus 10 volt.
Okay. By chance, if I make this 10 volts to plus 5 volts, just for the sake, will D2 will be forward or reverse?
Sir, forward.
It will be forward bias. If I make this plus 20 volts, how much?
Forward.
It will be forward or reverse?
Forward.
It will be reverse bias because this is 20 plus 20. So a higher voltage is there on the cathode side and a lower voltage around 10 volts is there on the anode side. So the diode will be reverse bias. The anode
Yes, sir.
voltage should be greater than the cathode voltage by an amount of 0.7. So please keep these diode concepts in your mind, because since we are dealing with diode transistor logic, diode is likely to be there. Okay. So the next case is, that is case 3, that is D1 is going to be reverse biased and D2 is going to be forward biased. And in the last case, you can see that when you give high voltages on both the terminals, that is D1 and D2 are going to be reverse bias. So I want you to put these 4 cases in your notebook. Now, if you look at case 1, that is when I give 0, 0, if I give 0, 0, both the diodes are on. Both the diodes are on. So the voltage at the output is going to be the voltage across the diode. It is going to be the voltage across the diode, that is 0.7 volts. Here in this case, since both these diodes are actually in parallel, D1 and D2 are in parallel, even if one of them is on, still the voltage drop across the diode is going to be, so this will be 0.7 volts. Here also for 1 0 it will be 0.7 volts, and for 1 1 it is going to be 10 volts. Now why? If both are 0, current will start flowing and it will flow into these two diodes. So as you know, when the diode is forward biased, it offers extremely low resistance and the voltage drop across the diode is going to be 0.7. And if you look at this point we are measuring the voltage between point C and ground. So this point is at 0.7 and this is at 0, so that is why we have 0.7. Here the current will flow, but all the current will flow only through this diode. The current flowing through this diode is 0. So if you look at point C, if you look at this point, the condition at this point C is something like this, that is, we have a short circuit or we have an on diode in parallel with the off diode. So off diode is open circuit, on diode is short circuit. So the voltage drop across point C, so I will show one diode here. So the voltage drop at point C will be just 0.7. Similarly here, this is just the case C is just the reverse of case B, and case 4 is Then off. That means we are having point C. Now here we have an open circuit in parallel with the open circuit. Here we have point C. So here we now have an open circuit in parallel with a diode which is on. So that is going to be plus minus 0.7. So the voltage here at point C is going to be 0.7. So you can see that at this point, this is a low value, this is a low value, this is a low value, and this is a high value. So basically what you get is an AND operation, that is VA VB 0011 0101. We get an output which is low, we will say 000, and high we will say 1. So this is with the basic operation of an AND gate using diode transistor logic, DTL. So two diodes and one resistor can be used to make an AND gate. So please draw all these 4 cases, and once you are done, just write done in the chat box. This is very much essential. Please draw it. Any doubts in this? Please unmute and ask. So you can actually build this gate on a breadboard. You have to just take one diode and one resistance. Resistance can be just a 10 kilo ohm resistance. I think building the gate is not very difficult. Hemant, are you following this?
Yes, sir.
Don't worry, now things will start becoming complex. Any doubts here? Please unmute and ask. Yes, Vishwas, you have any doubts? Vishwas, I can see you in the spotlight. Do you have any doubts?
Sir, I guess your phone is with your laptop, that's why.
Sorry, my phone is
Beside your laptop, that's why there was disturbance. Also, your camera is on.
that is fine. You should know how I look, otherwise you will forget me. Okay, so should we go ahead or do you want me to wait? Asmita, you are done drawing or you want me to wait?
Yes, sir, done.
Okay, still I'll wait for a minute or so that everybody copies it. Okay, so let's go ahead. So now I think everybody is convinced that this thing works as a AND gate. So let's look at some more methods. So this is the concept for a OR gate. This is the concept of a OR gate. Now you can figure this out for yourself. We can just check here itself by writing VA and VB and the output at C. So 0 0 1 1 0 1 0 1. So probably we can also write diode D1 and D2. What is their state? So when this is 0 0, so if this is 0 and this is 0, so here what will we get? So the diodes are going to be reverse biased. So the diode is going to be reverse biased. Now let's say that you give here, this is 5 volts and this is now 0. So D1 will be forward biased and D2 will be reverse bias. If I interchange the combination, this is 0 and this is 5, then this will be reverse bias, this will be forward bias, and if I make both as 5, both diodes will become forward biased. Now in case both are reverse bias, the current flowing through this I is going to be 0 because the current in this branch is 0, the current in this branch is 0, and as you know this is a node in a circuit. By KCL, this is I1, this is I2, so I is equal to I1 plus I2. I hope you have not forgotten what I have taught you in BEE, at least the KCL and KVL. So that holds true here also, because this is a node and these are the branches of the circuit and they form a closed loop. So that's the reason why at a node in a circuit, KCL I is equal to I1 plus I2. Here we are not actually considered about the closed looping inside the circuit, because We are not applying KVL, we are applying KCL. So as far as KCL is concerned, we are interested in nodes and not the completeness of the circuit as such. So that's the reason why the output here is going to be 0. But when this is the case, that is the second case, some current, this will not be 0. I1 not equal to 0, and hence I will also be not equal to 0. And that is why some voltage will drop here, and that will give me a high output. Similar thing will be here, and when both are on, you will get even a higher current, so that is going to be high. So low, high, high, high means basically that's going to be 0, 1, 1, 1, which is basically the output of a OR gate. So you can just note this table that I have drawn, VA, VB, output D1, D2. I think that should be sufficient. So I have just drawn the AND gate here for your reference, because you can see that this resistance R1 and R1 is connected between output and VCC, and for a OR gate, R1 is connected between output and ground. So connection wise only that is the difference. Connection wise only that is the difference. So please note this. This is a OR gate, but we want NAND and NOR also, so we want some inverter action in between. So we want some inverter action in between. Karthik, can you just unmute yourself?
Yes, sir.
Have you done AC analysis of common emitter configuration?
No, sir. Actually, analysis is not started yet.
No, AC
Means
analysis.
we are no.
H
We have
parameter
done
model, RE
DC.
model. Have you done that?
No, sir. Actually, we are right now we are doing numericals on MOSFET.
So you must have done BJT, right?
Yes, sir.
So in that only it is there, no?
एक्चुअली सर ने मतलब ऐसे टॉपिक वाइज लेसन वाइज ये नहीं लिया, मतलब सर ने बीच में मॉड्यूल 1 का लिया था, बीच में मॉड्यूल 4 का लिया था, ऐसे हुआ था.
Okay, ठीक है, whatever. So I'm just asking for information so that it is easier for me to explain it to you. Okay, ठीक है, you can mute yourself. So once you are done, just type done in the chat box. Vishwas, are you there?
Yes, sir.
Are you following this?
Yes, sir.
So this is actually the technology, okay? Uh, why this emphasis is there, because till now whatever we designed, we considered the gate as a black box. That is, the gate had a fixed functionality. Now here we are trying to investigate inside the gate. So I still remember a question asked by Mandar. Mandar, are you there? Mandar Kulkarni. Mandar Kulkarni, are you there? Okay, because of some reason he might not be there. But I remember in my very first lectures, Mandar had asked me this question, sir, what is there inside the gate? So now what I am trying to show you is what is there inside the gate. So you know that the gate can be used to make mux, demux, counters, encoder, decoder, this, that, so many things. But now how selecting a particular technology would actually affect the performance of the gate? And now we are going to see what are those performance parameters. So that in that sense this study is very important, and after doing this study you will be, the outcome of this study is that you will be able to now see or read the data sheet of any IC. You will be able to see or read the data sheet of any IC. So probably in the next class I'll just put up some data sheets on the screen and I will ask you to read it. So as an engineer you should know how to read data sheets, because data sheets will have specifications, and for a certain application you should be able to see the specifications and suggest that instead of this we can use this IC also because this is slightly cheaper, that way. Okay, so let's go ahead.
Sir,
Yeah,
so why do we connect the resistors means like that
What?
only
Shubham, can
between
you
output and
speak a bit louder please? I could not hear you.
hello?
Yeah,
So why do we connect the resistors in specific positions only for AND gate and OR
so
gate?
that
Like
we,
I didn't get that.
so what happens is, in this case we have to pull the output to high. So we want a voltage drop, then only we will get some voltage at the output. See, what is this logic 0 or logic 1? What is this 0 and 1? 0 means 0 volts and 1 could be high high voltage. Low voltage and high voltage. So low can be as low as 0 and high means it can be any high value which is greater than 0. So as far as these technologies are concerned, the high values are 3.3 volts, 2.2 volts, 5 volts, and in very rare cases 10 volts. In diode transistor logics we had 10 volts, but from TTL onwards we have been scaling down the power supply voltages. So the function of the resistance is to drop voltage, or rather cause voltage drop. That is the function of the resistance. Only when voltage drops across the resistance we will get some high voltage. If there is no voltage drop across the resistance we will not get any high voltage, and the voltage will drop only if current flows, and current will flow only if diode is on. So in a way they are all linked. Shubham, are you getting this thing?
Yes, sir. So does the value of the resistance matter in means like change in AND gate and OR gate, or it remains the same for all the gates?
The value of the resistance matters in the sense, so okay, so that's a very good question. Operation wise the value of the resistance doesn't matter at all, meaning I'll tell you, just a minute. Yeah, so it's a very good question and thank you for asking that. So everybody should just listen to this question. Shubham is asking, does the value of the resistance matter? Operation wise, no, but yes, if you look at these parameters, fan out, power dissipation and delay, then the value of the resistance matters. Now, if the resistance value is high, then your power dissipation will become high. if there is a capacitive load, for example, if this is followed by an amplifier, so amplifier will generally have a capacitance at its input. So R into C will cause a time delay. So in that sense, the delay will increase. The fan out also depends on this. That means if the resistance value is high, then the value of the current flowing through this is going to reduce. So in a way, if the current flowing is going to reduce, then the fan out also reduces. So then the question arises, should we keep the value of R1 low? So the answer is again no, because if you keep the low means what? It can be as low as 0. So if you keep R1 as 0, then there will be no voltage drop. And point C will be permanently be connected to ground only. So in that sense, we cannot have R very low also, we cannot have R very high also. So we need to have a moderate value considering these three parameters: fan out, power dissipation and delays. Does that answer your question, Shubham?
Yes, sir.
And this is where the IC manufacturers will play with us. They will say that okay, the fan out of the chip is 10. That means the OR gate can drive 10 more OR gates. Some people will make this value of R1 high, and then they will say that fan out is less. Now, technology wise, if you see, high resistance values are easy to make, but very low resistance values are very difficult to make. So that is why you will get lesser fan out ICs at cheaper cost and higher fan out ICs at higher cost, because the technology that is used to make this resistance is changing. So that's where they actually decide the cost of the IC. That's how they decide it. Have I been able to bring some clarity, Shubham?
Yes, sir.
Thank you. Sir, your voice is cracking. Akshay, Karthik, is my voice cracking?
No, sir, it's clear. I think the network issue is from his side.
Akshay, just try to adjust your phone in certain direction, and if the cracking continues, just let me know. So then I'll adjust something here. Okay. So should we go ahead? Now, this is the basic of the OR. So please draw these cases for the OR gate as we drew for the AND gate. So what is very peculiar is when the switch is open, that means diode is reverse bias. Here it is forward bias. Sorry, here also it is reverse bias. This is reverse bias. This is forward bias. This is FB. This is RB. And here both are forward biased. So please copy this, and I'll give you another 5 minutes to do so.
Hello, sir.
Yes.
Sir.
Yeah.
Sir,
Who
can you
was-
please explain the concept of darshan, sir?
Yeah.
Can you please explain the
Concept of
concept of fan in, fan out? Fan in, fan out.
fan in, fan out. I will tell you in brief, but though we are going to cover this later on also, but still, let's say we have a AND gate. Okay, so the number of AND gates that we can connect at the output of its own type. So this is AND, they are all ANDs, and this is also a AND gate. So you can see that if I can connect maximum of 4 AND gates at the output of one AND gate, then the fan out is 4. And the reverse way, the other way around, that is, if I have an AND gate, the maximum number of AND gates that I can connect at its input so that is going to be fan in. So there is a limit. We cannot connect infinite number of AND gates on the output side of another AND gate. That means the output of one gate cannot be the input of infinite number of gates. There is a limit on that. And that is called as fan in or fan out. Did you get this, Darshan?
Yes, sir.
But more on this, I think when I will do the specification, I will do that. Here you understand only the operation of the gate. Akshay Salunkhe, sir, I had a doubt. The internet provider promises a certain amount of Wi-Fi strength, but in reality it is always less than what he said. That's what they actually do, because TRAI allows them to do such things. So it is a illegal thing which works in a legal way. That's my answer. So in continuation with what Akshay is saying, that one of my students, Vikas and his group, they had made a project to actually determine the continuous use of Wi-Fi strength, and that system used to raise a query with the service provider that, look, we have measured this much and you have promised this much. So there is a difference of the signal strengths at these points of time. So you have to now compensate for us, or probably extend our pack or something like that. So our very electronics department students have done that project. The project guide was, I think, Professor Velankar.
Sir, but the internet provider actually listened to this?
Sorry, no, they don't listen to anybody. I told you, no, it's a illegal thing which works legally. Any such things, as you grow up, you will come across such things, and the sad part is you cannot do anything about it. We'll be back at 11:10. Okay, so let's go to the next thing. Karthik, just doing a time check. Are you able to listen and see the slides?
Yes, sir. So now you are not audible.
Now I will be audible. So we saw the circuit of and we saw the circuit of OR. But what if I want NAND and NOR? That is my question. Okay, we want NAND and NOR. So you must have done this particular analysis of CE amplifier. So this is the CE amplifier, and here if you do a quick small analysis, the gain of this circuit can be easily derived in this way. So basically this is RE, this is the AC model of the circuit. I'm sure sir will do this. Then this is your collector, this is base, and this is emitter, this is RE. The current flowing through this is IB, the current flowing through this is IC, and this is IE. And you can very well check that in a transistor IE is equal to IC plus IB. So that gets satisfied. The resistance RC is connected between this point collector and VCC, but AC wise VCC is considered as ground. This is your V out, and this is going to be your V in. Of course there will be an RB somewhere here. So we can have, or we can establish some relationship between V out and V in. So we can write V out is equal to minus ICRC and V in is equal to RB plus RE, RB plus RE into IB. And as you all know, gain is always output upon input. So if I take the ratio of this IC will have beta times of IB, and this IB gets cancelled out, and what we actually get here is minus beta RC upon RB plus RB. So the gain equation, I'm just writing it down here, it is minus beta RC upon RB plus RB. So the values of RC and RB will actually control the gain of the transistor. But that is, the gain is not very important in this case, because we are not working on continuous signals, we are working on digital signals. This, you can see here that there is a minus sign. The minus sign indicates that there is a 180-degree phase shift between input and output. Input and output are 180-degree phase shift. So that's what we get here. Now you may have questions, why did I take this as minus ICRC? Because the current is not flowing this way, the current is flowing out of the ground. That is why, since the direction of current is not from a higher potential to a lower potential, It is from a lower potential to higher potential. So that is why I have appended the minus sign. And that gives me 180 degrees of phase shift. So now I know if I pick up a AND circuit, so this circuit, so if I apply a 0 here, or if I apply a low value here, I'll get a high value. That means if I apply a sine waveform like this, here I should get a sine waveform like this. Or in other words, in the case of digital, if I apply something like this here, I should get something the other way around at the output. So this circuit actually works like an inverter. This circuit actually works like an inverter. So we know AND gate plus inverter means it's a NOT gate. AND gate followed by a NOT will give me NAND, and OR gate followed by a NOT will give me NOT. So this is what an inverter will look like. So please copy this circuit, and in case of doubts, please unmute and ask. That might be the same doubt of everyone else. What
Hello,
is this?
sir.
Yes, Asmita.
Sir, can you please explain the inverter part again?
Inverter part again, you can see that AV, the gain equation has got a minus sign, right? Minus sign means what? V out and V in are 180 degrees out of phase. That means V out is minus AV into V in. So if it is just AV into V in, we say that input and output are in phase. But if there is a minus sign, we say that input and output are 180 degrees out of phase. That means if you give a rising signal, you will get a falling signal at the output. And if you give a falling signal at the input, you will get a rising signal at the output. So this operation is called as inversion. And that is why this circuit acts like an inverter.
Okay, sir. Thank you, sir.
And this AC model is from EDC. So the model of the transistor that I have used is the RE model. There are many other models also, H parameter, hybrid pi, but for explanation sake, this is good enough. And this is which configuration? This is common emitter configuration. You can see emitter is common to both parts, input as well as output. So if you model the circuit as a two-port network, here you will have the current flowing inside will be IB, the current flowing here would be IC, and the current flowing here would be IE. Here you have input voltage as VBE, output voltage as VCE. So please note, this part we saw just now, and these two circuits is nothing but the circuit that you are seeing here. So when I connect AND in series with this NOT, so the previous circuit in series with this circuit should give me NAND gate. That's how we develop the circuit. Here the BJT, the transistor is used as a switch. So given circuit acts as a switch, provides 180 degree of phase shift, Input and output are 180 degrees out of phase. Hence circuit behaves like inverter. So once you have copied this, just write done in the chat box. Should I go ahead? Krishna Prasad Menon, are you able to follow this? Mandar, are you there? Mandar Kulkarni?
Yes, sir.
Mandar, I hope you remember your question that you asked. What is there inside the gate?
Yes, sir. I was asking you right now, but I thought
So
it may be a not
so
great
now
time to
it's
ask.
gone inside the gate, and what did you suddenly see? You suddenly saw that there is lot of EDC inside, right? So that's the fun part of it. So everything is integrated. That's why your second year courses are basically your foundation level courses, and you should know each and everything in detail. ENAS, EDC, digital design, they are all your fundamentals. You should know certain things in it by heart.
Hello, sir, you are on mute.
How is that possible?
So now you're audible.
Yeah, I can see that, but automatically it's going on mute. I don't know. Please don't mute me. Okay, so you can see here that this is your diode, and here you are having your transistor, and the logic that you are implementing is a NAND gate. So that is diode transistor logic of a not NAND gate. So I think that's pretty simple. Please draw this. So if you want to look at this operation, let's look at the first condition. If I give 0, 0, then these diodes will be reverse biased. So the current that is coming from here, so I1 let's say 0, I2 is also 0. So whatever current is coming in, it will not go on this side, it will not go on this side, it will go straight away into this I. So basically the base volt, so this current I, so what will flow here is IB, and most of the current will flow through this. Now you know that this I would be something in milliamperes, and IB, as you know, is in microamperes. It's very small. So again, most of the I will be available across R3, which will give me a voltage drop here. So the voltage drop at this point would be I into R3. That's the voltage drop. And if this voltage drop is greater than VBE of this transistor, then this transistor would turn on. This transistor would turn on. So if this transistor turns on, then what we will get here is this IC would start flowing through this IC, and the voltage that you would get here is VCC IC will be, so it's just the integration of diode transistor. But you can see here there are resistances. Okay, so there is a problem in making resistances. I told you that it requires huge area. Resistance requires a huge area. So what we actually do is, I'll wait for 2 minutes till you draw this diagram. Just erase certain things. I EDC पर है. Okay, so let's go to the next diagram. So I think you can generalize a OR also. OR will be just a resistance here. That's it. So you will get rid of this and put a R here. That's it. So Tanishq, are you getting that?
Yes, sir.
So if you want to just convert this NAND to NOR, all you need to do is remove this R1 and connect it here. That's it. So that should give us a NOR, and of course the NOR table is, as you know, that's how it is. So I just wanted to do this to just get in more clarity. I'm just removing this R1 for the time being. Let's make this as it is. Please understand this circuit very well. Okay. Now here, since I gave 0 0, this is not reverse bias. I mistakenly wrote it as that, so it's forward bias actually. So the current that comes from here splits into these two parts, and you know that the base impedance is very high, so that's the reason why the currents will not flow here, because there is a resistance here. This resistance is around 10 kilo ohms or something, and the forward resistance of the diode is just 100 ohms. So all the current will flow in this direction, and the current that actually flows into this IR2 is almost equal to 0. So here you are having a 0 base drive, so Q1 is off. If Q1 is off, then the current flowing through this IC will be 0, and whatever is VCC will come at the output. So basically you gave 0 0 and you got a high output. We can try one more, that is the last one, that is 1 1. So if both are 1 1, this IR2 will not be equal to 0. VBE will be high. This Q1 will not be off, it will be on. So IC will not be equal to 0, it will flow through this Q1. And since the transistor is on, it offers a very low resistance path. That is why this point is as good as connected to ground. And that is why you get a 0. So that's how it works as a NAND. So you can try out the middle two cases. Okay, so let's go to the next part of the circuit. Now there is something wrong with this circuit. So what is wrong is that for any gate, output impedance should be low. Output impedance should be low. Now, why it should be low? Because then if output impedance is low, we can expect more current at output. We can expect more current at the output. And more current means better fan out. More current means better fan out. So, with a view to get better fan out, now we will slightly modify this circuit. First difficulty was resistance, and the second thing that we want is better fan out. So now I am going to the next circuit. So you can see this was our previous circuit only, the same one as before. But you can see that this R2 has been replaced by two back-to-back diodes. Now the reason for that is because the diodes, when forward biased, the diode presents a low resistance to I1. So it presents a low resistance to I1. So we don't want this resistance to be high when I1 is trying to flow through this to the base, and when we do not want I1 to flow through to the base, we want the resistance to be high. So if we use a fixed resistance, this gives me a fixed resistance, and this combination will give me low resistance and high resistance depending on whether I1 tries to flow or I1 does not try to flow. So if I1 tries to flow to the base, it should have low resistance path, and if I1 is not trying to flow through to the base, it should have high resistance. So here you get both high and low resistance, and the resistance changes depending on the operation. So please don't draw the first one, don't draw this circuit, draw only this one, in which you will show the circuit and replace R2 by D3 and D4. Now see, I am trying to replace resistances by diodes, so more diodes.
Hello, sir.
Yes, somebody said something. Does anybody want to ask some doubt? Please ask.
Yes, sir. It's Prathamesh.
Yes, Prathamesh, you want to say something?
Sir, could you please explain the part where why do we require to uh, uh, place the diodes in place of the resistance?
Okay. So let's check this combination. Okay, let's have here 0 and 0. So this will be forward bias, this will also be forward bias. So now the current is, all the current that is flowing through R1 is trying to flow as I1 and I2. So it is not, the current I is not supposed to flow through this. So when you don't want this I to flow through the diode, still there is a resistance R2 here, right? This I can get divided into I1, I2 and IR2. Now what designer says that anyways you are not using, you are not interested in how much current is flowing to the base. You want that all the current should flow through the diodes only. So for that purpose, this R2 should be high. When I am giving 0, 0, this R2 should be high. When I am giving 1, 1, I want that this all the current should pass through this. So at that time, I want R2 to be low. Now the problem with a fixed value of R2 is that we cannot change the value suddenly in between. Once you fix the value, it is remain R2 only, it will not change. So we want a device which would change its resistance based on the input voltage that it gets, and that device is diode. So when current tries to flow through this R2 branch, the resistance is low, and when the current does not try to flow through this branch, the resistance become high. Did you get it?
Oh, yes, sir. Yes, sir. Thank you.
So fixed value, that's where I have written here, the value here is fixed, but we want high and low depending on the value of I1. So if I1 tries to flow in this branch, then we should not obstruct it. We should make a low resistance path. If I1 is not trying to flow through it, then we should have a high resistance in that place. But technically speaking, if you put a fixed value of R2, you cannot change it suddenly in between unless you use a device which can do that. So that device is diode, nothing else, because diode has a characteristics like this. No? So here you will get low resistance, and in the reverse bias you will get a high resistance. So we use the property of the diode to do that. Okay, so let's go to the next circuit. Now I have kept this same circuit as it is. Now you can observe this part of the circuit. Especially the point C is where we are measuring the output. When transistor Q1 is on, impedance offered is low. Why? Impedance offered is low because the impedance offered by transistor Q1 is very low when it is on. So this point and between this point there is low impedance. When transistor Q2 is off, between this point and this point there is a resistance RC which is in kilo ohms, and this will offer resistance in ohms. So it happens that during logic 1 we get high impedance, and during logic 0 we get low impedance. Now this is also a problem because my output impedance should remain constant. It should not change depending on the value of the logic level. Whatever may be the logic level, my impedance should be the same for both the cases, and typically it should be as low as possible. So that is the problem. To solve this problem, we use something called as totem pole arrangement. This is called as totem pole arrangement. It is desired to have low output impedance in both high as well as low states. So this is what we want. Hence, we use totem pole arrangement. That means the circuit, the part of the circuit which I have shown in green is now replaced by this thing. Now why this is called as totem pole? Because totem pole is basically something like this. This is the arrangement. This is called as totem pole. So, and it's a part of native Indian American culture. So during their festivals, they just stack these structures like this, and they are, this arrangement is called as totem pole. So I don't know why, but the designers felt that this part is like a R, this part is Q1, this part is like a diode D1, and this part is like Q2. So RQ, D1 and Q2 are arranged in totem pole arrangement. So I am not expecting you to draw this figure, but yes, you should write this and draw this circuit. So if I change the output of this transistor, instead of Q1, now I will have two transistors, Q1 and Q2. This output you can take it from here or here, actually does not matter. It's up to you. So now why we are going for totem pole arrangement? In the Viva they may ask you why you are going for totem pole arrangement. That is to ensure that the output impedance is the same during both high and low conditions at the output, and not just same, it should be as low as possible. So we know that diodes and transistors, when they are on, offer extremely low resistance paths, and that is the reason why above the output also we have connected diode and transistor, and below the output also we have connected a transistor. So when the current flows from either one of them, the current will have low resistance path. So let's go ahead. So what we are now planning to do is that we want to replace this output side by this particular circuit. But as you can see, here one transistor was controlled by 1 VBE voltage, that is R2. So the voltage drop across I2 R2 was actually controlling this Q1. But now there are two transistors, Q1 and Q2. So we require a control circuit such that both the transistors are controlled. So for that purpose, now we have to go for the next circuit. So this is called as, so this is my totem pole, and I go for another circuit called as phase splitter. Because the two transistors of the totem pole output stage must switch oppositely from one another, the base input signals of each must be 180 degrees out of phase. What is the meaning of this statement? The meaning of this statement is, at any given point of time, only one of them should be on. That is, if Q1 is on, Q2 should be off, and if Q1 is off, Q2 should be on. Only one of them should be on. And to control that operation, we require another transistor that is called as Q3. Now you should be able to see that instead of now diodes, more transistors are coming up. That is why we now actually shifting from diode transistor logic to transistor logic. That's what we are actually trying to do. This is achieved with the help of phase splitter. Phase splitter consisting of transistor Q3 ensures that either Q1 or Q2 is on. For example, if here we have 0 or low base voltage, then Q3 will be off. If Q3 is off, then all the current will flow into Q1. So Q1 turns on and Q2 turns off. If I give here high voltage, so this will turn on Q3. If Q3 turns on, then no current will go on this side. All the current will flow through Q3. A voltage will drop across this resistance, and this will act as VBE for Q2, and Q2 will turn on and Q1 will turn off. So this by applying a suitable base voltage at Q3, we can control Q1 and Q2. That is what we have written. Phase splitter consisting of Q3 ensures that either Q1 or Q2 is on. Both are not on at the same time. Why did we use Q1 and Q2? Because we wanted same impedance during both logic 1 and logic 0. So, but we replaced it with totem pole, but totem pole came with another problem of control of transistor Q1 and Q2. So we introduced now phase splitter. Now at this point we can give our input of the previous AND gate and get a NAND gate. So in short, phase splitter plus totem pole gives me an inverter with low output impedance for both logic 1 and 0 outputs. Inverter with a low output impedance for both logic 1 and logic 0 output. That's what a phase splitter and totem pole will do. Please copy this, whatever is there on the slide, and especially what I have written below in red. Any doubts in this? Unmute and ask. So what are the key points? We are not operating transistor in active region or anything. We are operating it as a switch on and off. That is why I am talking about transistors in terms of on and off. When you are thinking about amplification, you have to think about other modes of operation also. But here we are simply talking about transistor is on and transistor is off. So they are like switches. That's it. If the base voltage of the transistor is low, then the transistor will turn off. If the base voltage of the transistor is high, then the transistor will turn on. The transistors that you are seeing in the circuit are NPN transistors. NPN transistors or NPN BJTs. Okay, Karthik, Vishwas, should we go ahead? Tanish, Soham, Yash, are you there?
Yes, sir.
Sir, wait for 2 minutes.
Yes. Sure. Tanvi, are you following this?
Yes, sir.
I am going a bit slow, but if you want me to go even slower, just stop me. Ruchira, are you getting this?
Yes, sir.
Parth, what about you?
Yes, sir.
Yes, sir means getting or not getting?
Yeah, getting it, sir.
Okay. Good. So things are going to be even more complex now. So see, gate looks very simple, but to achieve that functionality, it's a task. So now we just don't want a simple inverter. We want an inverter with low output impedance for both logic 1 and 0 operations. So to ensure that, we need to put totem pole and phase splitters. Okay, let's go to the next thing. Now you are able to see such kind of arrangements. So basically, if you just see two diodes which are connected like this is N, this is P, and this is N. So actually this combination works like a NPN transistor. It works like a NPN transistor, and this model of the transistor is called as Eber-Mols model. It's called as Eber-Mols model. This word you can find in book called as Streetman, Bench Streetman. It's a Prentice Hall International book, and of course you can find this in Yarbrough also. But about the model you will find here, Yarbrough uses this model and says you can use this as NPN. So this is N, P and N. So you don't have to actually remember this Eber-Mols model. You can just see that two back-to-back diodes with anodes common. So that anode, this is N side, this is P side, this is P side, this is N side. So we can club the P sides and take one common terminal out from there and call it as base, and so this side will be emitter, these two P's would be base, and this would be collector. So this is emitter, collector, and this is my base. Please draw this. So now you saw that we had this kind of structures, okay. We were giving our inputs through the diodes. So now our effort is to reduce this structure into a transistor. So we want to replace those diodes into a transistor. So it's 12:07. It's time for our second break. So let's meet at 12:17 and complete the TTL part. And in case there are doubts, you can just unmute and ask me.
Hello.
Okay, so let's start. So taking this model forward, so this is the place where we saw back-to-back diodes. So let's say that if it's a 3 input and then this can be ABC. If it's 4 input, it can be ABCD. If it's a 5 input, it can be ABCDE and so on. So what you can see is we have a combination of D1 dy, we can have a combination of D2 dy, we can have a combination of D3 dy, dot dot dot, we can have a combination of dx dy. So you can see this is one NPN, each one of these is a NPN. But out of these NPN transistors, base is common to all the transistors, and this dy, that is the N region of each transistor, is also common with every other transistor. So what happens is we have 1, 2, 3 X emitters, we have X emitters, one base and one collector. We have X emitters, we have one base and one collector. So that gives rise to such kind of a circuit. We have 1, 2 X emitters, one base and one collector. So this is a multiple input emitter BJT. Multiple emitter input BJT. So it's a BJT only structure wise, but instead of taking out one emitter pin, we take out E1, E2, E3, EX, then we have base and then we have collector. So collector is slightly bigger in size, even base is, so the geometry of this device is slightly big as compared to the normal one, but yes, we can have multiple emitters like this. And this is what we actually do. So we combine these two. So this, if I connect it here, I should get a NAND, and that NAND we will call it as TTL NAND, because we have transistors, transistor, transistor and transistor, with this one additional diode just for isolation between above transistor and below transistor. So basically this entire DTL now converts to TTL. This diode transistor logic goes to transistor transistor logic. So no need to draw the last diagram, draw only the first two. Draw only the first two. So circuit wise, this is like a multiple input, and this is an inverter. When you add in AND gate in series with the inverter, you should get a NAND. You should get a NAND. And if you want a NOR, then I'll just remove this R from here and put it across here. That will be my NOR. Anyways, you just only draw the first two. That's it. The second diagram is the equivalent of the first one. Okay, so let's go to the next slide, and that is something that we all have to draw. So you take a multiple input emitter, a phase splitter plus totem pole, which acts like an inverter, and that should give you a 2 input NAND. So now you can see that there are some typical values here, 4K, 1.6K, and so on. So when I connect this thing here, I get the third one. So now no need to draw first two, you can only draw the third one, because first two you have already drawn. And this VCC also we can join, and that is precisely this. So again I am just reiterating it. This is a AND gate plus please copy this. So if you are done with the last circuit, just write done in the chat box. Current is not supplied, it is the base of current flowing. The current starts corrupting, comes on, starts drawing a current from zero. That is what I correctly complementary. So, am I audible? Similarly, you can try out some wires. Current from here. Current is asked for. Current to the base of the transistor. Current will stop. That's what comes through the that's I am not audible because can you hear me now?
Hello, sir. You are not audible.
Audible now? Okay. So can you hear me now?
Yes, sir.
Okay. Some network problem, nothing more than that. So let me just share the screen once again. Yeah. Just a quick check. Can you see the screen?
Yes, sir.
Okay. So let's move on to the next thing. So if you want the explanation of this each and every transistor wise, that's what here it is. If it is 0 0, the emitter base E1B, this should be E2. So E1, this is E2, this is B, and this is C. So E1B, E2B is on. So you can see if this is 0 0, this is on. This is 0 1, this is on off. So this is 1 0, this is off on. 1 1 means off off. So wherever there are zeros, emitter base junctions are going to become on for this transistor Q1, and IBs are going to be low in the first three cases. That is, this is the IB of Q2, which is also the IC of Q1, and then we have Q2 base emitters. So the base emitter of Q2 is off, and on. Q3 is off, and on, and finally we have Q4. So this and this and this, if you see, all ons will give me ones, all offs will give me 0. So if you just take any case, like the last case, let's say this one, then these junctions are reverse bias. So that is what we get. So if this is reverse bias, the gate IB will be supplied to this Q2. So that is why we say it's high. If this is high, then Q2 will turn on. If Q2 turns on, Q3 will turn on, and Q4 will turn off. And when that happens, if this is off, the output gets connected to ground, because Q3 offers a very low resistance. And hence the output is 0. So please copy this table. Diagram you have already drawn. Only the table you have to draw. So as such, this table gives the complete explanation of the circuit. If this base emitter is creating a problem in understanding, you can just say whether Q2, Q3 and Q4 are off or on or off, whatever. When we say Q2 is off, that means base emitter junction of Q2 is reverse bias. When we say Q2 is on, we say base emitter junction of Q2 is forward biased. So once you are completed with this, just write table done in the chat box. So how will this table look for a NOR gate? So all ons you will replace by off, all lows you will replace by high. So off will become on and on will become off. Low will become high and high will become low. And as far as output is concerned, 1 will become, that will become 1 0 0 0. Or what you can do is just only the input, the first circuit, the AND. So this part of the circuit is actually AND. So inverter part will remain the same. So what we will do is so this will be your A and B, and the same thing so this is your okay. So let's go ahead. So the next logic that we have in place is CMOS. So the primary advantage of CMOS technology is that we can optimize these designs, that is we can optimize CMOS logic for area. So we can have low area design. We can optimize it for speed. So we can have very high speed designs, and we can optimize it for power. So area, speed and power are the process corners of any technology. They are the process corners of any technology. CMOS. What is the meaning of CMOS? Complementary metal oxide semiconductor. Actually it is CMOSFETs, but they just skip the FET part of it. It is understood that it is a FET logic. So I'll just write here FET is understood. So what's the basic difference? Yash, can you answer this question? What is the basic difference between a BJT and a FET?
No, sir, not got it yet.
Okay. So in a BJT, the equation which governs BJT is IC is beta times of IB. So the base current controls the collector current. That means the input is generally applied at the base and the output is observed at the collector. Both input and output are current quantities. So we call, so BJT is a okay, I can see some answers, but I think you can listen to what I'm saying right now. BJT is a current controlled current device. So I am talking in terms of two-port network now. BJT is a current controlled current device, and when it comes to FET, FET can be JFET, it can be MOSFET, it can be FinFET, whatever. So we have equations like ID is equal to Kn by 2, VGS minus VTH the whole square. So this is like a saturation current equation. So you can see that what is being controlled is current only, but it is being controlled with voltage. Here what is being controlled? Current only, but it is being controlled with current. So FET is a voltage controlled current device. It is a voltage controlled current device, and BJT is a current controlled current device. So in a way, voltage control current is much better than current control current, because electric field currents will respond to an electric field in a much better way than another current. So in that sense, FET action is better, and here we make use of both NMOS and PMOS. Now why? Because PMOS is a good transmitter of logic 1 and NMOS is a good transmitter of logic 0. So what I want you to do is, today we will only see this basic diagram of CMOS. CMOS has got a PMOS network consisting of only PMOS transistors, and it has got an NMOS network consisting of only NMOS transistors. So at the top we will connect PMOS, below we will connect NMOS. PMOS network is always connected towards VCC, or in many cases it is also written as VDD, and NMOS networks are connected towards ground. So if at all you know this, the symbol of PMOS is like this. So this is your source, gate and drain, and the symbol of NMOS is like this: source, drain and gate. So you can see that for a PMOS the arrow is pointing inside, and for a NMOS the arrow points outside. Current always enters through drains to the source and comes out. So this arrow is the direction of the current, and here the current flows in this way. NMOS and PMOS network, the common point between NMOS and PMOS networks is called as Vout. So that is the common point. The inputs are applied to both NMOS and PMOS. The inputs, the same inputs, let us say that there are two inputs, A and B. So A and B will go to PMOS, A and B will also go to NMOS. PMOS is a good transmitter of logic 1. That is why if I want to connect output to VCC, it has to be through a PMOS. If I want to connect output to ground, then it has to be through a NMOS. That is my NMOS network. So good transmitter of logic 0. PMOS network, since it is connected between the central point and VCC, it is called as pull-up, and NMOS network is connected between central point, this is central point, and ground, it is called as pull-down network. So this is the basic topology of CMOS logic. That is PMOS, all PMOS are connected between VCC and output. All the NMOS transistors are connected between output and ground. Inputs, the number of inputs going to PMOS and the number of inputs going to NMOS are equal. PMOS is a good transmitter of logic 1 and NMOS is a good transmitter of logic 0. That is why they are connected in pull-up and pull-down respectively. So please draw this circuit for now, or the basic topology of the CMOS. This is called as topology. So all CMOS circuits will look like this. Another advantage of CMOS is it has fixed design procedures. Okay, and we can have almost zero static power dissipation. We have almost zero static power dissipation. That is because either VCC current flows like this, either current flows from VCC to output, or it flows from output to ground. There is never a current which directly flows from VCC to ground. This current is not there. And hence the word static is important. The static power dissipation is almost zero. That is when the transistors are not switching, at that time the power dissipation is zero. And this is really very important because most of the times our circuits are off. They are in the off state. They are not switching. And in the off state, they should not consume unnecessary power. So this is the major advantage of CMOS technology over TTL, that their static power dissipations are zero. For TTL, even if the transistors are not switching, still it will consume a significant amount of power due to the presence of resistances, diodes and BJTs. Here, since the transistor used is also different, the topology is different. Because of all this, the static power comes out to almost zero. Of course, that is in an ideal case. So this is in an ideal case. Otherwise, if you have done MOSFETs, then there are something called as short channel effects. If the MOSFET is really very small, then the problem there is something called as subthreshold conduction or hot electron effect or impact ionizations. These are the probably the effects because of which we do not get static power dissipation. But yes, if we say that the device, the transistors are slightly bigger in size, then these short channel effects will be minimal or zero, and hence in that case we can achieve zero static power dissipation, of course at the cost of area, but that is fine sometimes. So please copy this block diagram, and if you have doubts, unmute and ask. So I am just rubbing out certain things. So for the next class, I want you to revise NMOS operation and PMOS operation from your EDC course, and what is VTH, what is the threshold voltage. Threshold voltage is the voltage required to keep the PMOS on or the transistor on. So I think the entire design procedure we'll do it in next class along with PL and PLAs, and then conclude probably chapter 5. But there is lot of designing in CMOS, so I will not hurry in that case. Okay, so that's it from my side. I have downloaded the attendance. Thank you very much. Yes, you all can log out. I have taken the attendance.